All right. Recording is now in progress and we will go on. Now, as we were just talking, we were in lecture 6, we had discussed some ways to work on the initial conditions. We kind of worked out that you could express this pair of equations, number 1 and number 2, as a linear system, as a matrix A, which is labeled here, multiplied by an unknown vector X and another known vector B. And in MATLAB, you can quickly solve this as the inverse of A times B if you want to find the vector X, which is going to be the first component, alpha 1 and alpha 2. And of course, those values are solved by hand here. So if you are, if you're at the midterm, say, which is 2 weeks from now, and you want to solve this, it's another way to go about solving systems of equations. In this case, 2 equations and 2 unknowns. Then we mentioned that a difference equation with 0 initial conditions is LTI. But if you have a non-zero initial condition, it is not time invariant. That's because the initial condition doesn't shift with the actual difference equation. So when you shift the difference equation, its behavior will change in terms of when it does its response in time. But since the initial condition doesn't shift, that means that the system will actually have a different behavior when the behavior of the system actually depends upon the time of the input or the initial conditions. And so it's not time invariant. Now we're talking about eigenfunctions. Eigen is a German word. It's a special function. The special property of this function is that when it is input to any LTI system, the same function will come out. The main difference being is that it will be scaled, it will be multiplied by something, and that something could be possibly complex. So that is the eigenfunction property. It is the basis by which all linear time invariant analysis occurs, and we'll find out how important it is because it's the fundamental underlying property of the Fourier transformation. So we're going to demonstrate that in fact x of n, if it's a signal, and that signal is the complex exponential e to the j omega n, which is by Euler's formula, cosine omega n plus j sine omega n. If we input that to any linear time invariant system, it will come out. We're saying that e to the j omega n, the complex exponential with magnitude 1, is an eigenfunction. That's what the claim is. Okay, so we take any linear time invariant system. I'm going to call that linear time invariant system h of n. And we're going to input it to the systems, to a system. Sorry. All right, and so if we put that signal in, what I'm saying is that what comes out is the same function multiplied by complex constant. We're going to call the complex constant e to the j, h e to the j omega. This is a complex constant. It's the thing that satisfies the definition. Remember, it comes, the same function. This is the same function coming out. And this is the possibly complex constant that multiplied it on the output. So I'm saying that the output of the system, which is y of n, is equal to the input of the system. This here is x of n, multiplied by a complex constant. That complex constant is h e to the j omega. So this is just sort of the definition. And so in the case of a linear system, right, we'll just jot down the convolution here. K goes from minus infinity to infinity. All right, and so if we take the system as h of k and our input as x of n minus k, that would give us e to the j omega times the quantity n minus k times h of k. Sum, k goes from minus infinity to infinity. All right, now what can we do to this sum in terms of this e to the j omega n term? The sum of, exactly. The sum over n is not, k is not a variable there. So it's a constant with respect to that. So we can rewrite that sum. So sum goes k from minus infinity to infinity. And we could take this e to the j omega n out in front, e to the j omega n. And then we have h of k, e to the minus j omega k. All right, so this is actually a number. this thing here is actually a number. And I'm going to call that number h e to the j omega. And that's what this equation right here says. So again, if you call this entire sum a number, which it is, like this is, you know, like this is consider this to be an integral, right? This is an integral over k. So you play, it's going to come out to be a number, right? And so then whatever number this is, it multiplies the original signal. This is x of n. So we just proved the eigenfunction property, albeit it might kind of not seem like it. But if you take all of the values of the impulse response, which is the linear time invariant system, because h of n is a representation for any linear time invariant system, right? We plugged it into the convolution equation, which is a representation for any linear time invariant system. We come up with this infinite summation, in this case, over e to the minus j omega k. We're going to call that a number. That number is h e to the j omega. It depends on omega. And it depends on the system, which we're using, which is h. But that number just multiplies, right? So that's the eigenfunction property. This ends up being a lot more, it kind of just looks like a bunch of math right now, but it actually ends up being quite important. Because we can use this in interesting ways. Yeah.
Just out of curiosity, so for like a wireless signal that's sent or received that needs to be amplified by like an antenna, does the input like have to be an eigenvalue in those cases so that you're just getting pure amplification?
So in communication theory, the usual for signaling theory and kind of broadcasting and communication of signals, usually there's a very specific form to the function that you send that is going to allow for optimal behavior in some criteria, so in some metric. Usually it's the optimal bandwidth, like you're achieving the largest amount of communication, like information is being transmitted as quickly as possible. That's what we call bandwidth. And in that construct, we create signals that have, usually it's bipolar signaling, but those signals that we create there are actually combinations of eigenfunctions. In fact, we'll find that any signal is a combination of an eigenfunction, because any signal can be represented as a sum of complex exponentials, because the sums of complex exponentials are sinusoids. And when can we represent any signal? Well, that's not any signal. Can we represent any absolutely integrable or absolutely summable signal as a sum of sinusoids? The answer to that is yes, because we have mastered the Fourier transform, which tells us that any signal, periodic or not, if it's periodic, not only does it have a Fourier transform, it has a Fourier series. If it's not periodic, it only has a Fourier transform and no Fourier series. But in both cases, we're representing a signal in terms of a sum of trigonometric functions. And every one of those trigonometric functions is a combination of two complex exponentials. Like if I want to write down cosine, I could write it down as e to the j omega n minus e to the plus e to the minus j omega n times 1/2. I just want to, that's my way of writing cosine of omega n. Is that okay? No one has a problem with that, because you can just see if I write down e to the minus j omega n, like here, I get cosine of omega n minus j sine of omega n. And then if I sum vertically, I get 2 cosine of n, the sines cancel. That's why I have the minus half out in front. And this is a different way of writing cosine of omega n. So when you study the Fourier series, or you study the Fourier transform, realize that you're actually studying linear combinations. If you think of them as trigonometric functions, that's great, but actually they're combinations of complex exponentials. And we're looking down here a little bit deeper at these fundamental underlying functions, eigenfunctions that make up these trigonometric functions. Does that track with everyone? Okay. Eigenfunction examples. We have a system. Is it linear and time invariant? H of n is equal to delta of n minus nd. Okay, so is this linear and time invariant? is it written as an h of n? Okay, you don't even have to look at what's after h of n. Because it's written as h of n, it is linear in time invariant. Because h of n is only represents linear time invariant systems, right? And so we can go on and do analysis and find that, but I want you to kind of short circuit it. If you ever see it's written as h of n, you know it's already linear in time invariant. Okay, let's compute the convolution sum for this. Well, it's a delta function. What attribute will we be using to calculate the convolution? What property? It's a sifting property or a sifting integral. If you were to do this in 3111, a sifting property. And so we know that this delta function only takes on a non-zero value when k is equal to nd. And so this is the actual convolution problem. So I've chosen to write the problem as h of k, which is just substituting a k for n, and x of n minus k, which is why we have e to the j omega quantity n minus k here. And then we have this summation. Now we know that the only non-zero part of this summation is the index k minus nd equals 0, or k is equal to nd. In that case, we only plug in nd, then we have delta of 0, e to the j omega, now n minus nd, right? So then we have all this happening here, delta of 0, e to the j omega n times e to the minus j omega nd. It's e to the j omega n times this. Is this a complex constant? nd is some number, right? So like this, what if it were n minus 1, right? So nd would be the number 1 here, right? So if this were delta of n minus 1, nd is just some number. It's our lag index, right? So nd is an actual number. It's a constant that we know. So that means that this thing here, e to the minus j omega nd, is a complex constant, right? It has magnitude 1, and what is its phase? What is the phase of the number e to the minus j omega nd? Remember, for a complex number, we represent it as r e to the j phi. We call r its magnitude and phi its phase. So what is the phase of this? This complex number has magnitude 1 because that's r, and it has phase. Phi is minus omega nd. So if we were to plot it in the complex plane, it would be on the unit circle. So the unit circle has magnitude 1. And then my cursor goes away. And then what would its phase be? A phase is counterclockwise rotation with respect to the positive real axis. So we would go around the positive real axis to whatever coordinate omega nd is, and we draw our vector. And that would go out here. And this would be, well, actually, since it's minus omega nd, it would be clockwise. So, but it's kind of, I want to, so you'll need complex number theory to live here in this class. As you can see, lots and lots of complex number theory. So we need to, what's going on here? Oh, that was undesirable. All right. So yeah, we need to know about the complex plane and how to plot our numbers and all of these special terms. Like there's lots of special terms with complex arithmetic. And so I just use them freely. So like I'll sound like I'm speaking Greek if we don't kind of review our complex numbers. Okay, so that complex constant is, I'm going to call that h e to the j omega, and of course that is its value. In fact, there's a minus sign that needs to be here. That is its value. Any questions on that? I'm going to make this slide just a little bit bigger, just maybe a little bit easier to read.
Excuse me,
Okay.
that was,
Is there a question online?
yes.
Yeah, hi.
Would you get that zero that you plugged in the delta function out here. Delta
Uh,
of zero equals-
This part in the middle of the slide?
yeah.
Okay,
No, no,
yeah.
the last
So
one.
I kind of went through that really quick, but I wanted to evaluate this convolution here. And so to evaluate that convolution, this should, so keep moving my cursor. Okay, so I see that the index here is not written right. So this is a sum over k, h of k, x of n minus k. We want to evaluate this convolution. So we have the function delta of k minus nd, and we want to, and it's a sum over k, right? So we want to figure out when this, it's going to be equal to 1 when k minus nd is equal to 0, using the definition of this, of the delta function. So when it's equal, when k minus nd is equal to 0, the delta function will have the value 1. When k minus nd is not 0, it'll have the value 0. So the only term inside this sum that's non-zero is wherever this delta function occurs. So to find out where this delta function occurs, we have to find the value of k that makes the argument here evaluate to 0. And so from the lecture notes, I suggest that we go and solve this linear equality. And so if we solve it for k, we get k equal to nd. And we say that when k is equal to the value nd, this delta function will assume the value 1. And when it is 1, we'll have a 1 in this position, and we'll actually have a non-zero output. So then I rewrite this sum as k goes from nd to nd, because there's really only one value, delta k minus nd e to the j omega n minus k. And then we plug that value of nd in, and that brings us to this step here. Does that make sense?
Oh, yes, please. Thank you.
All right, fantastic. And so I will, so this process is this sort of, this is a technique for solution. So whenever you end up with a function, you don't, and it's got some non-trivial thing inside of its argument, my suggested technique for solution is to figure out when the argument will have the values you care about. For the delta function, you want to know when the argument, when this function is going to be equal to 0, because that's where, when it's non-zero, it's when it takes on the value 1. For the step function, you kind of have to use the definition again, like so. Like we had something like this, 6 minus n or something as a homework problem. U of 6 minus n, you kind of want to figure out when that function, what's going on here? This is really, this driver support needs to be looked at. So we had something along the lines of u of 6 minus n as part of one of the potential problems that you got on the quiz or the homework. And so, you know, we want to figure out when that's 1, when it's 0. It will have the value 1 when 6 minus n is greater than or equal to 0. You'll have the value of 0 when 6 minus n is less than 0. And the technique for solution here is to solve this inequality for n. And so you have different ways to solve it. I always like to just keep n on the left side to just, it's simpler for me intellectually. So I just multiply by -1, but that means you have to flip the direction of the inequality. So I write it like this, and that would be a -6. You put 6 on the other side. So that's, so when n is less than or equal to 6, this step function will have the value 1. When n is greater than 6, it'll have the value 0. That's how, that's the technique solution for solution that I suggest that you apply all the time for all of these step functions or delta functions, because it will always work, and it's always just using either the skill solve an inequality or solve a linear equation. So you're just solving an algebraic equation in either case. You're not trying to do anything special about remembering when to reflect and when to time reverse or anything like that. You're just solving a linear equation. All right. Yeah.
Just to clarify, so I'll make sure I'm thinking about this right. So when you have your h of e to the j omega n, your eigenfunction is not only scaled by the real component of this complex number, but the phase represents the shift.
Yeah, exactly. So if you're, so in this case, it's a the input is complex exponential, right? This is our input. So it's complex valued input, right? And since it's being multiplied by a complex, in this case, with this particular system, it's being multiplied by a complex constant, right? That complex constant is specifically e to the minus j omega nd. So that means that the scale, the magnitude part is 1. So it's not changing the magnitude of the output in this case. In this case, it's only changing the phase. And that is exactly what you would predict. This system here, h of n, is a delta. So it's actually shifting, the input is being shifted such that x of n goes in, but x of n minus nd comes out. So in fact, the value of the input hasn't changed in magnitude in any way, but it has changed in phase. In fact, every one of the frequencies that we might want, if we were to construct x out of frequencies, omega, like as its Fourier transform, every one of those frequencies would be phase shifted by minus omega nd. That's what that's saying. Right? The frequency, it's like this would be the discrete frequency that's in the signal. So we're getting to the point where we're going up to the Fourier transform. And this tells us about sort of the relationship between impulse responses and their Fourier transforms. But yeah, in this, all I'm saying here is the phase is being shifted. Now, sometimes I take a moment to say this. Does everyone realize that if you multiply by a complex number in the plane, 2 complex numbers you multiply, it's just rotation? Right, yeah. So if I have, say if this is R1 e to the j phi1, and I have another z, so this is z1, let's say I have a z2 is R2 e to the j phi2. It's not like multiplication like you might think of it. If you multiply these 2 numbers, z3 would be the multiple of the 2. Well, it's just R1 R2 e to the j phi1 plus phi2. And since you're changing, like that means their phases add, so they're rotating. So complex multiplication is rotation. And if one of them has unit magnitude, it's only rotation. Like you're only rotating the other thing, not changing its magnitude. You're only adding its phase. I don't know if sometimes people don't talk about that, but it's kind of an interesting property. Like complex arithmetic, when you multiply 2 complex numbers, you're actually doing rotation in the 2-dimensional plane. Hopefully it's not blowing any minds, but it was good. It kind of blew my mind. I used to do a did you know kind of lecture where you kind of say all these kind of things that are like subtle details that often get not discussed, and that was part of the did you know thing. Yeah, well, we'll have, I do a little bit of that as we go sometimes. Because the eigenfunction applies to all LTI systems, linear combinations of eigenfunctions are also LTI or also eigenfunctions. So now we're getting to the point that a linear combination of an eigenfunction has to be an eigenfunction, right? Because the eigenfunction property is satisfied for both versions, and the system itself is LTI, right? So if I put in one complex exponential and it gets multiplied by some complex constant, I put another complex exponential, it gets multiplied by a different complex constant. Linear systems satisfy superposition. So if I add up the 2 numbers and they get scaled by 2 different constants, homogeneity and additivity, linearity, it has to also be an eigenvalue or an eigenfunction rather. And so what does that mean? Well, we showed that if we take the sum of a complex exponential and its complex conjugate, we get a cosine. So does that mean sinusoids are eigenfunctions? So we're saying that if so a complex exponential is an eigenfunction. We just proved that. Now I'm saying if you have a linear time invariant system, linearity also requires that linear combinations, or say the sum of 2 eigenfunctions, is also an eigenfunction. if we take a complex exponential and add it to its own complex conjugate, which is what I'm doing right here, that's a function that we all know and love. It's a real valued function, not complex. All the complex values cancel out, right? Because we just we went through that right here, right? We actually did that. I kind of jotted things down quickly, but if you take e to the j omega and you add it to the second line, e to the minus j omega, the cosines add and the sines cancel out. So no complex parts anymore. Yeah, this is, yeah. In fact, all that stuff is kind of inextricably linked together in a very tight analytical loop. So it's kind of like a dog chasing its tail, depending on which part you grab on. Anywhere you start will be consistent with any other part. Like you can get, it's sort of this, you can get to any point in complex theory if you start at any other point. So if you start at Euler's equation, you can get the trigonometric stuff from Euler's equation. I don't know if anyone did this, like you can actually prove Euler's equation by just looking at the trigonometry of the complex plane. That's kind of like how I like to prove Euler's equation. It's just a right triangle. What do you do? Okay, Euler's equation, right triangle. So here I am in the complex plane. This is the real axis. So if I have a complex number, the real part tells me how far I would go up in the x. And the imaginary part tells me how far I go up and down on the y-axis. And so if I have some number z right here in the plane, I'm going to call this z, and I'm going to write z is equal to a plus j times b. And I want to represent that trigonometrically, then I write an angle here, phi, because that's how I wrote it on the other side. And then it's going to have the length on this axis here, it will be a, and its length on this axis will be b. And so the length of this, if we call this r is equal to the square root of a squared plus b squared, and phi, of course, is the tangent of phi is equal to b over a, and so phi itself is the arctangent of b over a, which is equivalent to saying the arctangent of the imaginary over the real. But how does this prove Euler's formula? Well, what if we wanted to just talk about this real part here? Well, what's cosine of phi? It's a over r, right? What's sine of phi? That's b over r, right? And so if we wanted to, so if we have r e to the j phi, and so is equal to a plus jb. Well, and then we divide through by r, we have e to the j phi is equal to a over r plus jb over r, and we make a substitution, and then we're done, right? This is cosine of phi, and this is j sine phi. And Euler's formula no longer is some complicated esoteric thing, it's just trigonometry, right? It's just trig. It's like, this is the like high school trig. This is not, it's just, yeah, I'm sure you all saw that. But anyways, so we're here, we're talking about eigenfunctions. Linear combinations of eigenfunctions are also eigenfunctions. So that means that all trigonometric functions with arbitrary frequency, omega, are eigenfunctions. So sinusoids and cosines and sines are the same function. We call them something different because it's convenient for the purpose of analysis, but a cosine and sine are the same function up to a phase shift, right? Phase shift of 90 degrees, you'll get the same function. So if you put a sine or a cosine into a linear time invariant system, that same frequency will come out. It will come out, but it'll be multiplied by a complex constant. The complex constant, if its magnitude will change the magnitude of the sinusoid, and its phase will change the phase of the sinusoid. So if you have a circuit modeled as a linear time invariant system, you put a sinusoid into it, does the sinusoid always come out? If it doesn't explode. Yeah, so it was linear, right? If it explodes, that's a non-linearity, by the way, right? So it's like perfectly explainable by the theory. But yeah, you put a sinusoidal excitation into a system, a sinusoid will come out. Any linear time invariant system, and you can, it's just Very true. Any questions about that? All right, so they do not change frequency. That's a critical thing. The frequency that you put in is going to be the frequency you come out, but it can change the amplitude and the phase because of this possibly complex constant that multiplies in. All right, so I have a example in MATLAB that shows, I guess, what do I do? It's kind of an interesting example because I generate a completely, see H of n, this line of MATLAB code, which is actually very small. I will amplify it. Okay. And so this line of MATLAB code is the one that actually is testing the eigenfunction property. What does this line of do? Well, I said H of n is a random sequence of numbers. I generate a completely random sequence of numbers for H of n. So our system is a finite impulse response system consisting of random numbers. That means it's anything. I mean, I'm not choosing any of these numbers. It's an indiscriminate choice of the system. And then I do a convolution of H with X, where X, in this case, is a cosine whose frequency is 22 pi times 1 over 25, right? So its frequency is 1 over 25, so it means it'll oscillate once every 25 samples, right? So its period is what? 25 samples, capital N is 25 samples. If I put it into the system, what comes out? Well, we can see over here, you put this system in, this function in, and then this function comes out, and there's a phase shift. So it's a randomly chosen H, so that H has actually got it's scaled things by approximately 5 here. But it's randomly chosen system, and it's a verification, sort of a sample-based verification that this theoretical property is in fact true. Everyone understand what's being tested there, what that experiment says? I basically I picked a random system by specifying an arbitrary and random impulse response. And I input a sinusoid to it. And a sinusoid of the same frequency came out with a different magnitude at a different phase. And it doesn't matter what system I choose. I chose it completely randomly. I could do this a million times, a billion times. I could do this for the remainder of my life. And the property would still be true. Right? That's what this experiment shows. So it's basically verifying with some numerical work. Like, again, we should be able to verify everything numerically that we say, and we'll come back to that very shortly. With real experiments, with real numerical experiments, either in MATLAB or however, computation machines abound, or they're all around us, so we can just verify. So I'm going to save this as the last lecture. So is there any questions about this before I transition to our discrete time for a transform lecture? Lecture 7. So I see some things in chat. If folks that are online would like questions answered, you're going to have to go ahead and unmute and ask those questions. That's my request. Because I'm just going to go to the next lecture slide. Okay, so lecture 7, which is not opened in this way. Okay, this is our third and last representation that we need to know for the midterm. Representation for what? Representation for a linear and time invariant system. It is the frequency domain representation for a linear time invariant system. The frequency domain representation for a linear time invariant system basically takes H of n and represents H of n as a signal in terms of a sum of complex exponentials, or if you like, sinusoids, because complex exponentials and sinusoids are not differentiable. Sinusoids are just linear combinations of complex exponentials. All of the equations in a textbook are in terms of complex exponentials. So if you've seen equations from the past where we used cosines and sines, they're the same equations, but they're actually, if you think of those equations as symmetric. If I do a sum over complex exponentials that go from -1 to 1, I'm actually constructing an e to the -1 j omega n and an e to the 1 j omega n That's actually 2 cosine omega n, right? So you can write these equations both in terms of sinusoids or in terms of complex exponentials. The more general framework is complex exponentials, and that's the framework of all of the mathematics of the textbook. So that is the framework we use in both lecture and in all of our work in the class. Let's see, we've lost our cursor again. By the way, we just had the opportunity to complete quiz 3. Homework 4 is available to you. Homework 4 is a sort of some of this stuff that we've been working on, but it continues on into the discrete time Fourier transform, which is the subject of this lecture, the discrete time Fourier transform. Both the forward discrete time Fourier transform and the inverse discrete time Fourier transform. Note that there's a lot of letters here, D, T, F, T. There are 4 letters. This is not the discrete Fourier transform, which is very distinct. This is not the DFT. The DFT is what you would calculate in MATLAB if you were to calculate FFT or something. This is not that. All right, from the book, chapter 2.7 or sections 2.7 to 2.9 from chapter 2. You have a homework, and then next Friday, anticipate a quiz in Canvas. And the midterm is approaching. Yes, 2 weeks from today, we'll be convening to have the midterm. So these are specific sections from the textbook that we'll be covering. And this is a reminder, we've had this slide on each of the last 3 lectures or slide stacks. This particular slide stack is dedicated to the frequency response representation of a system. So the Fourier domain representation. There is a 4th representation, the Z transform. That is not going to be on our midterm. We haven't time to cover it before the midterm. Okay, so in terms of defining the discrete time Fourier transform, we take a little journey. And so let's make this a bit larger. Some math here. We have the continuous Fourier transform here in the left corner. And in the right corner, we have the inverse continuous Fourier transform. These are both continuous integrals over the variable, in this case, t. We integrate over t. We end up with a function of frequency or of omega. Here we integrate over omega and we end up with a function of t. So we're integrating over one variable and it's gone when we do that integral. We define the spectrum and the phase of the signal that we're calculating here. So the spectrum is the result of the Fourier transform. And the phase, which theta of j omega, is the arctangent of the imaginary over the real, which is just, and remember that all that we're doing here is we're writing down the phase of a complex number. I keep trying to remind students that, okay, this is a function of omega, but all it is like if I wrote z is equal to a plus j omega, z is a function of omega, right? Right. So then I can write z of omega, or maybe I write z of j omega is equal to a plus j omega, and all of a sudden students get confused. Oh, I'm just writing down a complex number. This is just a complex number. The number is different for any, if I give you a value omega that's 0, you get a different number than if omega were 1. But it's just a complex number. So I want everyone to look at this and not be worried. This is just a complex number, right? You can measure its magnitude. We call that the magnitude spectrum. Why is it a spectrum? Because for every value of omega, you'll get a different magnitude. You'll get a different magnitude complex number because it's a, it's part of the, it'll change. When we calculate the phase of that complex number, we get another function, and that is the phase spectrum, right? So the magnitude spectrum and the phase spectrum is just a way of writing down the magnitude of a complex number, but now that complex number can change in value. It's not a fixed complex number. It changes with the value omega. Okay, so now we talk about the discrete domain. We have not capital omega, but little omega. And when we write things down, we write it as e to the little j omega. So the notation changes, right? This is how we would notate a Fourier transform. This is how we notate a discrete time Fourier transform. Note very importantly, we have parentheses. So this is a continuous. So it's, I'm going to write it again as if I was repeating myself. Continuous function of omega. This is a continuous function of omega. Why do I keep writing that down? This is in discrete signal processing. A lot of people get confused and think that this is a discrete function. Like it only takes on like omega needs to be an integer. It does not need to be an integer. Only when we write x of n, that's an integer thing. This is not an integer thing. This omega here could be the value pi. It could be 1/2. It's a continuous function. I want to be very clear about that. Doesn't take on values only at integers. It takes on values everywhere. And we write it down this way. We take the values of x of n, we sum from -infinity to infinity over the values of n, and at each of those places, we multiply by e to the minus j omega n. That is the discrete time Fourier transform. That is its definition. And of course, if you make the substitution using Euler's formula, that's equivalent to multiplying by this. All right, the inverse discrete time Fourier transform. So I used to spend a lot of time on this because I find this incredibly peculiar. Does anyone look at this here? So I look at this equation and I immediately have objection to it. I look at it and I say, what? This can't possibly be right. This equation is wrong. For exactly the reasons I just said to you. I'm going to show you an example of why this should be wrong. Okay, so I have an integral from a to b of x dx. What does it come out to be? Well, it's x squared over 2 plus c, if you want to be technical, and you evaluate it from x equals a to x equals b, right? Okay, so this is a continuous function, and you get out a continuous function. So when we integrate continuous functions, we tend to get out continuous functions, right? You integrate cosine, you get sine. You integrate sine, you get cosine. Continuous in, continuous out. That makes sense. Makes a lot of sense. What am I, is this continuous? I just told you very much, I made a big deal out of telling you this is a continuous function of omega. That's why we have to apply continuous integration to integrate it. Well, what's on the left-hand side here? This is a discrete function of n. It only takes on values at integers. Everywhere else, it's defined to be 0. Now, when I saw this equation, it blew my mind. I'm like, well, professor, you're obviously wrong. Nope. Input not accepted. I've taken my integral calculus. I've taken my vector calculus. I've done integration so many times. I'm sick of the face of doing integration. I've never come up with a discrete function when I integrated a continuous function. You're wrong. This equation's wrong. Everything's wrong about this. I'm walking out. Done with DSP. All right, you can't do it. Well, you can't do that in pass. You can do that, but you can't do that in pass. Well, I suppose you can even do that in pass if you just know it all already, right? But anyways, I had a problem with this. And I used to go through class and actually prove why this is in fact correct. I've since found out that students actually don't care so much about that proof. Albeit I found it very riveting and thrilling. So I'm just going to say, it's true. It's true. It's surprising, but there is a mathematical proof that you can conduct that is in the textbook to a small extent, but you can extend it and make it very, very, you can expatiate on it and look at every possible detail. And yes, it cancels out everywhere except at indexes n when n is an integer. Wow, fascinating, riveting. It is now the definition of the inverse discrete time Fourier transform. That is how we go from the continuous function x e to the j omega back to a discrete function x of n. And we just embrace, we take that apparent inconsistency, or I guess it would be more specifically like unintuitive result, and we just embrace it and apply it. Any questions about that, other than the question that I overtly raised and then sort of summarily swept under the rug? Okay. So again, we have the periodicity of the DTFT. So this is a property that I want to show you about the DTFT that we actually ended up using quite a bit, and it's really important. And the property is that I'm claiming on this line that the DTFT is 2 pi periodic. That if it were a periodic function, right? Periodic, it's continuous, right? So we kind of have to write it as x of t is equal to x of t plus capital T, because it is continuous, right? It's got parentheses instead of brackets. So omega here is continuous. So I'm writing this as a periodic property. X e to the j omega is equal to itself after we add 2 pi to the omega argument. Well, that's very surprising. That means that if we look in the Fourier transform domain at the frequency response, it's only unique over a 2 pi interval, and then it just repeats itself forever. So that means if we ever need to look at the DTFT of a function, all we need to know is its values over a 2 pi interval, and we know its values everywhere because it's periodic. We can just copy them to the other locations. So here's the mathematical proof. We just like any periodicity proof, you plug in, we know the definition of x of e to the j omega, right? We just wrote that down. X e to the j omega is this thing here. So it's the DTFT. So I'm gonna write it down again. X e to the j omega. So capital X e to the j omega is the sum over all the values of n, goes from minus infinity to infinity. We take x of n and we just multiply it by e to the minus j omega n. And that's, you can always remember that's just how all Fourier transforms work this way. You just multiply by a complex exponential with a negative exponent. So now we're just going to apply that equation, but now we're plugging in, instead of omega, we have omega plus 2 pi. So we plug in omega plus 2 pi, but we previously had omega, right? That's all we do differently. And so now we can tear apart this exponential as the product of 2 exponentials, because we have a sum in the exponent. And so the first part of that product is e to the minus j omega n. Looks like a little typo there. And the other one is e to the minus j 2 pi n. All right, e to the minus j 2 pi n, I sort of tease apart in this little equation here. I kind of have an aside here where we kind of look at e to the minus j 2 pi n. That's cosine by Euler's formula. That's cosine 2 pi n. Cosine of 2 pi, what value does it have? Cosine of 0, what value does it have? Cosine of 10 pi, what value does it have? Cosine of any multiple of 2 pi, what value does it have? Any multiple of 2 pi, remember, cosine is periodic with period 2 pi, right? So 2 pi n that's a very fancy way of writing down the number 1. And that's something every once in a while, I ask you a multiple choice question on a test. And I'll write down x of n is equal to 2 pi n, and what's y? If y is equal to x, what's y? And one of the answers will be 1, but nowhere will it say 2 pi n. What's the right answer? 1. They're just 2 different ways of writing the same thing. And all you have to do is realize that, yeah, when I write the value 2 pi n, I'm not writing anything other than the value 1 down. It's just the value 1. It's a complicated way of writing the number 1. Lots of different complicated ways of writing the number 1, like delta of n minus 5 plus n plus 5. Complicated way of writing down the number of 1 at 0, right? It's just it's just lots of different ways to just exercise the basics of the basics of like all these properties. Anyways, we use it, and it's important to understand, because now this is just a number 1, and what do we get? Well, this is just the same thing as x e to the j omega. So we find that this equation, once we eliminate this term in red that's crossed out in red, and that's just x of n times e to the minus j omega n. And of course, that's our definition for x e to the j omega. So we've therefore proved that this function x e to the j omega is 2 pi periodic. It repeats itself, surprisingly. And let me ask you this: does the Fourier transform repeat itself? Is the Fourier transform a periodic function? In
No.
general, the Fourier transform, yeah, the correct. So in general, the Fourier transform is not periodic. So again, we have a behavior in the discrete domain completely inconsistent with what we know of the Fourier transform in the continuous domain, which is why this course exists. If everything were exactly the same, we wouldn't need to sit down and sort of reevaluate things when we start working on a computer. But if we want to properly interpret the output of the computer, we have to know why all the rules change when you start doing calculations on a computer and how those rules change. This is one of those important rules. The Fourier transform, when you calculate it on a computer, is periodic. Would never be periodic were that the case if we had a continuous computer. And then we'll understand more about that as we progress through the course. Chapter 4 will tell us more about that. Okay, so here we have an example for an x of n, and we want to calculate, let's see. In this particular case, I've just plugged in a specific value for a cosine. I guess I'm not going to specifically lecture on it. There's like a bunch of table lookups. But you know, the Fourier transform of a cosine is a delta function, right? So the Fourier transform, the discrete time Fourier transform of this. So the Fourier transform of a cosine looks like this, right? Cosine. So if I took the Fourier transform of cosine omega naught t, right? Do you remember that from 3111? The Fourier transform of cosine is a delta function. It's delta of omega minus omega naught plus delta of omega plus omega naught. That's the Fourier transform of a cosine. Well, it significantly changes in the discrete domain. You not only have those two impulses, but it's 2 pi periodic. So you have impulses that repeat every 2 pi on a 2 pi interval forever in both directions. So in this case, you get a unique pair of impulses from the continuous Fourier transform. In the discrete time Fourier transform, what we're talking about here, it's 2 pi periodic. So you can't just draw one impulse here. That impulse has to repeat over a 2 pi interval forever in both directions. So when we look at the DTFT tables, say this is the DTFT table, and we would look at, so here's for a cosine with a phase. You see it's a sum of an infinite collection of impulses. So all of a sudden you end up with all these huge equations, but if you remember that it's just 2 pi periodic, you realize that this huge equation is just taking the two pulses and then copying them and making, you know, an infinite train of them all together. So otherwise it's very easy to look at all these equations and get, you know, like overwhelmed by all the math. It's just not as complicated as you might want it to be. We can make it easier by just remembering the concepts and remembering the fundamentals that we have from continuous Fourier transform theory and translating those to the discrete time. So, all right, so the DTFT, as in the continuous Fourier transform, the continuous Fourier transform exists if the function is absolutely integrable, which means that you can integrate the absolute value of the function. So if you have a system, like if you can do this, then you can get h of t will have a Fourier transform. The same exact property exists, but it's now absolutely summable. You sum up all of the values and the sum of the magnitude of all the values. If it is finite, then its Fourier transform exists. Let me see. Can you take the Fourier transform of an unstable system? If it's unstable, it's not absolutely integrable. So therefore, it doesn't have a Fourier transform. I don't know, it sounds like a good problem to have on an exam.
Is time invariance necessary to take the Fourier transform?
No, time invariance is actually, so since that's affecting the n value, in the case of the DTFT, we're not even looking at the n value. We're only looking at the magnitude at a value of n, like the number that occurs at n. So we need time invariance, but to calculate the Fourier transform, we don't look. It doesn't affect. So whether the function system is time invariant or not does not affect whether it has a DTFT or not. All right, so we'll be adjourning. Well, we'll be adjourning right now. So we'll leave off right here as we have some questions to answer and things to talk about. And we'll be continuing from here on Thursday's lecture. We're about a quarter of the way through, so I do think we should be able to finish up that lecture by the end of our class on Thursday. So that would mean that we have our quiz. This is coming Tuesday. Now we have our midterm 2 weeks from now. So we're gonna have that quiz, we're gonna have another lecture, maybe talk about the project, but we're gonna have another assignment that's sort of a preparatory. And there's a lecture that comes after this, which is really the wrap all this theory up together. It sort of takes all of the 3 different topics, wraps it all together, and that's just sort of gets you ready for the midterm exam. So it's this lecture, next lecture, then prep for the midterm exam, then midterm exam. That's the schedule, okay?
So we're gonna have in-class times, review for the.
Oh, yeah, it's sort of, it's not a lot. So usually comes on the tail end of that, of lecture 8. This is lecture 7 that we're in right now. Lecture 8 is now we talked about the 3 different forms of linear systems. Let's talk about them all together. And how they all relate to each other. And then at the end of that lecture, it's just open mic, grill the professor, ask me anything you want. And, ask me how, you can ask me whatever you want. What's on the exam, I won't tell you. But it's just, it's meant for an opportunity to ask me whatever you might want to practice before the examination.
I just know I need to practice my own paper skills. I feel like I'm using MATLAB as a crutch right now.
Yeah, if you overuse MATLAB, it can actually get dangerous. And it can't, so MATLAB is it's a whack of the dog situation. Don't let MATLAB use you. Because MATLAB is a great computational tool, but it's also so sophisticated, it can actually get you into trouble. And so, kind of know, the thing that you might want to do is to know when MATLAB's going to do what you want, and know when MATLAB is going to be maybe a questionable path for solution. And for my advice on that is I would tend to try and avoid MATLAB when I have infinite length problems. Because it tends to lead to confusion more than help. So speaking of which,
So the reason that
let me just wrap this stuff up because I know we're gonna have a big
I'm
invasion.
finishing setting this up too, so that
Okay.
that way it has the exact same results.
Yeah, we'll get to the bottom of that. So I'm gonna stop the recording as well. And
Because I guess what was really weirding me out about
do
it
you want to stop? Yeah.